is you take your guess, put it in there, and you end up with this equation. So what's our goal at this point? Yeah, so we're trying to find K1, right? So this is just like, imagine you had a complex exponential source, right? The thing you would do is you would guess what the particular should look like, plug it in, and try and find K1. Now, as I mentioned, one of the nice things about having an exponential source is anytime you do, when you take the derivative of an exponential, what do you get? Exponential, right? Integral, exponential. So no matter what if you have R's, L's, and C's, they're all linear. They might take derivatives or integrals, but the keys are always going to leave something that looks like that in their place. So you're always going to be able to. And I haven't proven this, but you can kind of get the flavor that no matter what, you're always going to be left with that thing. You can divide it out. Why is it safe to divide that out? Never zero, because omega would either have, you would have to, well, in that case, you have to have a omega of minus infinity. So we're assuming they're finite. So then we do is we just go through and solve for K1. There's some algebra. And so what you do then is our particular solution for this new made-up source looks like this, right? Just plugging it back. You take your K1 and plug it back into your particular. Okay. So this is all, right? All this stuff is supposed to help us solve RLC circuits more efficiently and nicely. But unless you remember the very end of lecture last time, we're not quite there. Okay. And if we wanted to know, right, what the actual output of, because originally our source, right, our question was, how does it respond to a cosine? There's this nice property that if you take the real part of this equation, then you'll get the solution for a cosine source. So again, it's a weird, contorted, sort of strange argument, but it works really well. So why does that work? Why can you do this real part thing? So as a reminder, right, superposition, we know that if we take two sources, we apply them, then the output is just going to be the sum of the output of those two sources. So in other words, right, if we take this complex exponential source, which is the sum of a cosine and j times a sine, and we look at, maybe, for example, the capacitor voltage, and we get this expression as that total with those two sources put together, then this total right here is a complex expression. So it's got a real part, and it has an imaginary part. So all you got to do is kind of pull out this A, and you're done, okay? And so if you weren't here last time, you're probably like totally freaking out and like, this is the most insane thing I've ever heard. But if you were there, then, or if you were not there, watch the webcast, and I go through it much more slowly. But this is just kind of get us back where we were, right? Okay. So how do you actually go through and find the real part? So again, I have to reemphasize that, and hopefully if you've worked on homework 5, you've hopefully done one of these, or the reading assignment today. What you see is anytime you have one of these complex expressions, right, getting the real part is basically a matter of just kind of getting everything into the right form, multiplying all the complex part together, and then you can just pull it out by inspection. So the main thing to remember to do all this is that anytime you have a complex number, for example, a plus jb, you can also think of it as in polar coordinates, right? So you can write a complex number as a plus jb, or as r times e to the j theta. And so suppose you wanted to go from that form to that form, like you maybe forget what this looks like, but you think it might be a right guess. How would you prove that these two things are equal? Yeah, so you just take Euler's formula. So you'd bring this guy down, you'd have cosine j theta plus j sine, cosine theta plus j sine theta. And then, let's see, you would have to do, and you would plug in this right here. So you don't having the, and then you would plug these expressions in, and you would end up, if you do all the cancellations and the trigonometry, it's not much, then you'll get that, right? So you can establish that these things are true, but you can also kind of see them evidently and graphically that this is, showing that this thing and this thing you can't see graphically because it has Euler's formula. But once you have those and you understand the meaning right, the relationship, like if you ever forget the relationship between A, B, R, and theta, if you think of it graphically, then at this point, right, it's just clear that R is just the length of the total complex vector, and theta is just the angle, right? So this is going to be really important for the next week or the next couple days. So as an example, right, suppose we wanted to find the real part of this expression. What we've got right now is on the left, we have a number in rectangular form. And on the right, we have an expression which is in polar form. So if we want to combine it all into one nice thing, it's annoying to combine. You can't really, by inspection, do it. So what you want to do then is take whatever your rectangular part is and turn it into polar form. And so in this case, right, if you, the bottom part right there, 1 plus j omega RC, what we want to do is convert that into its polar form. So we'll do a more thorough example in a little bit. But basically, if you just plug in the stuff I have right here, right, and do some algebra, so R, right, for example, down here. So this right here basically represents the R. And so you guys hopefully can see that this is the R of that 1 plus j omega RC, right? Because it's just, although, it should be a square root. Oh, man. So you guys didn't catch me last time. All right. Well, our more thorough example in a minute, because I copied the slide from last time. So there should be a root over this. So does anybody have a Sharpie? Yeah. No, yeah. OK. And then this phi is just going to be arctan of omega RC. And let's make sure that's true. Yes. OK. And the only reason I put phi here and say phi equals arctan omega RC is because it'd be really annoying to write all that stuff up there. OK. Write that down, too. OK. So to find the real part of this expression, right, we convert it into that form. That form at the top is really nice because at that point we can just sort of multiply the two exponentials. We can add their exponents. And what we're left with is that in the middle. And so if we have that expression in the middle, and we want to know what's its real part, we use Euler's formula, and we get the following expression right here. So that's easy. You just bring it down. And so what's the real part of this thing? Yeah, basically just, take that away, and then you're left with answer. So in other words, right, superposition says we find this particular solution. This is our particular solution if you write it in a nice form. So is this form I would call rectangular form, right? So because you have kind of it's just the real part plus the complex part. And so what we know then is that the particular solution of our original problem with the original cosine source is just going to be this right there. So it's just the left side. OK. Except, of course, for this missing square root. OK. So that's kind of like a long way of doing it, right? So that's just another way of coming to the same answer you get with all the trigonometry. So our method that we described before that's sort of doing this, replace it with a complex exponential, go through and do all this stuff, and end up with a real, finding the real part of this expression. It's not the easiest way, because you can do that, right, every time you do a problem. But it would be basically like re-solving this over and over. You would always be kind of, it would be like always writing the ODE for a DC source and solving it. So it's going to be an easier way to do things. It's just less direct. And so what we're going to do is we're going to call that impedance analysis. And so the basic idea is based on